Hello, I'm Jason Sewall, and I'm going to present to you some work that was done with my colleagues John Pennycook and Doug Jacobson on ways to combine different metrics for performance portability and productivity for a holistic view of your codes so that you can get new insights into how a single code base or an aggregate code base may behave under certain changes. Is based on combining metrics. So let me introduce those to you. The first is the performance portability metric that John and I came up with a few years ago. This is based on combining the efficiencies for a given application on a set of platforms, and those platforms are some combination of hardware and software. This has a lot of properties. I won't go into great detail here, but it suffices to say that a code that gets a score of 0 did not perform on one or more of the platforms, and a score that goes to 1, that is 1, is the best possible based on the data that you have. And it's also worth noting that any result improves the metric, and any result getting worse lowers the overall score. The other metric is called code divergence, and this complements the previous metric. The performance portability metric allowed you to create what I call duct tape apps that are made of totally disparate pieces of code that are specialized for each platform, and that allows you to get a performance portability score of 1. Whereas a code that had a single code base may not get such a high score because it doesn't specialize. So code divergence is a way of talking about or quantifying the amount of specialization inside a code. And without, again, going into great details about it, duct tape apps have a divergence of 1. If they don't share anything at all, then they have a divergence of 1. And single source apps have a divergence of 0 because they don't specialize at all. And codes that have partial specialization fit in between. There are many different forms that specialization can take, of course, so I'm not going to go into great detail on that either, but just to give you a brief idea of what this looks like. This code on the left has some preprocessor directives, and it gets a divergence of 0.25 because some code is shared and some code is specialized. Whereas on the right here, there are two different files, and so nothing is shared at all, and this gets a divergence of 1. So, like I said, we have two metrics that complement each other, and they are scalar metrics. We can combine them together to produce something new and holistic that captures all the aspects of performance, portability, and productivity. We can combine the metrics like so in 2D. We select a common platform set, compute performance, portability, and code divergence for each, and then we plot them. What we've done here is actually swap out divergence itself for 1 minus divergence to create something called code convergence. And the reason for this is that it allows us to have positive trends moving toward the top right of the graph here, rather than have it be reversed in just the x-axis. So let's explore what this looks like. The best way to get started understanding how this sort of graph behaves is to understand how the extremes behave. And we'll explore that in the next few slides. To start with, let's talk about a common starting point. This yellow point up here represents performance portability of 1, but code convergence of 0. And this is what I referred to earlier as the duct tape solution. So this is a code that you've combined from several other codes that each target a platform. And by combining all the best implementations that you have something that can, by definition, achieve the best performance portability. However, the code convergence is by nature very low because they share no code. So this is our baseline. You can always have this. Down here on the y equals 0 or performance portability equals 0 axis, it's not very interesting because this represents a situation where one of the codes doesn't run at all or doesn't give the correct results at all on one or more platforms. So you're not generally going to see this unless you have a bug or a serial regression. This dot up here, where both values are equal to 1, is really where we want to be, right? This is the promised land where you have a single source that runs the best everywhere. And I'm not going to say that such a thing is impossible, but it's not very realistic to expect this for most codes. It's definitely the direction that we want to go into, but I think expecting us to get to this value of 1, 1 is probably not realistic. Okay, so given that duct tape solution, let's talk more about how we move in this space. An interesting thing that we want to explore is that you will take an application and plot it in this space. how do you transform it to get somewhere else you want to go if you have a goal? If you want that code to look differently, what are the ways you can move it around? So we know that performance portability and code convergence are linked, that there are trade-offs between them. We know that because when we construct the duct tape solution, right, we're taking a big penalty in code convergence in order to have these totally disparate pieces of code. And like I alluded to previously, it's very hard to imagine a transformation of a code where I have multiple pieces of code, I have multiple disparate code bases, and I find some way to reduce them all to one code, one single source that preserves all the performance, right? So moving directly across this along that performance portability equals one line is probably unrealistic. We could imagine perhaps that if someone had a heroic compiler that had a lot of backends and was very sophisticated, you could imagine that you could write some code and it's able to generate code for all these backends. But I think you can't expect that to happen in every case. We can be more systematic about how we discuss motion in the performance portability code convergence plane. So I've drawn arrows here that represent different directions, and we're going to go into more detail about them. Let's start by looking at the performance portability axis. So as you increase, you can say that this is a result of optimization in your code. Something has happened that is making your code run better, and that's the direction, that's the north direction that we call optimization. Conversely, if your code is running worse, then something has regressed, right? This may happen because of a performance regression that was introduced deliberately in your code. Perhaps you've chosen to adopt a platform that isn't supported as well with the current code base that you have. The other axis we care about here, of course, is code convergence. And as you move to the right, as your code convergence increases, that typically means that you are adopting some abstraction. And that abstraction allows you to eliminate specialized code. And as you move to the left, your code is becoming more specialized. You're increasing the divergence or decreasing the convergence of your code in order to have these specializations. Of course, people don't deliberately try to regress their code, but sometimes it's a side effect of the things that happen. And we're going to talk more in detail about sectors of this image and what it means to move in these directions. So if you look at this quadrant down here, this is the specialization regression quadrant, and this is almost never something that you deliberately do. This is a case where your code is increasing in specialization, but also decreasing in performance, or one of those elements at least. And that there are many different ways to think about what could cause your code to do this. But one example would be perhaps if you added a feature that perhaps negatively affected performance or didn't affect performance at all, but that increased specialization, right? And that feature, again, causes your code base and perhaps your performance to change, but that puts you in this region here. More interestingly is this specialization optimization quadrant. And this is a very typical scenario that I really want to emphasize. So let's say you have a very convergent code base, or a fairly convergent code base. But you have a performance portability score that you'd like to improve. Well, what you could do is identify which platforms are lagging, are dragging down the harmonic mean that computes performance portability. And you can begin to introduce specializations, divergence, that would increase the performance. And that represents you moving in this direction in the northeast to improve performance. Now, there are some considerations to have here. How fine-grained is the specialization mechanism, right? The slope of that line will depend on that. If you need to write a large amount of code, so if you need to introduce several new translation units, for example, several new files in order to support this, and perhaps abandon entire abstractions in order to get better performance, then you're going to see a large amount of code convergence drop, perhaps for very little performance portability increase. Whereas if you have a very fine-grained specialization mechanism that just allows you to do a few lines at once, then you will see a much higher slope line where you're getting a lot of performance portability for relatively little divergence, right? Moving along, we can talk more about the optimization axis. This is interesting because if you're moving strictly up and you're not changing the code divergence or convergence, then something is happening that is causing performance gains on a single or multiple architectures without you really having to do serious changes to the code. And this is very interesting. This perhaps represents better tools, or an algorithmic optimization that affects everything, right? That doesn't need additional specialization. Now, the place we all want to be here, of course, is in the optimization abstraction quadrant. Here, the code is both getting more convergent and more performant. And again, this is what we want. I want to caution people about being too optimistic about this happening. This does happen sometimes in relatively small amounts. I think when you find that backends are improving or tools are improving, there's new optimization passes and compilers, new tools or maybe new libraries that you can adopt. And this is a good place to be. This is a place that we want to see our codes going. But we should also not put too much faith on it and try to think of other ways that we can improve our code. Okay, the abstraction axis is interesting. If you're just moving strictly along the abstraction axis, you're probably refactoring your code in a way that that does not affect performance, right? So this is a common transformation to make. I've done this many times in my code. And again, you're eliminating code that no longer needs to be specialized, and it's making the code base more compact and easier to maintain, but you're not necessarily targeting performance. Moving along to the regression abstraction quadrant, this is interesting because here you're increasing convergence, but your performance portability is dropping. And these sort of things often happen as you adopt an abstraction that carries with it abstraction penalties. Right, so you may see that you're making a trade, and this is often a conscious trade that you make to have a simpler code base, but that nonetheless suffers because certain subtleties that are important for some platforms are lost. MiniMD is a code that's been around for a long time. It's a proxy for lamps. The original OpenMP code is CPU only. And a few years ago, John actually wrote MiniMXHD, which was a version for Xeon Phi and for Xeon that was highly vectorized and very tuned for those architectures. But both of these codes only run on CPUs, and so that's why they live down here. You can see in the performance portability equals 0 axis, because they don't run on the GPUs that we want to run on. The Cocos code was developed by Sandia, and it's the best GPU performing version of the code that we have. This OpenMP 4.5 code was one that was written by John and I a few years ago to test out OpenMP 4.5 features and things like that, and that supports both CPU and GPU. And again, we see that same trade-off here. Cocos codes are almost always very convergence 1 or very, very close to 1. But this OpenMP 4.5 code trades off a little bit because it has some target regions that aren't supported by the CPU or that aren't useful for the CPU, and some CPU code that is not used on the GPU. And again, we can see that there's a slight trade-off here. OpenMP 4.5 runs a little better on the CPU, not quite as well on the GPU actually, but overall it's buoyed by that and has a higher performance portability score while having slightly lower convergence. Hydra 2D is a code that I've looked at many times, and it's a CEA benchmark code. I optimized it several years ago, starting out using OpenMP. And I used auto-vectorization to start with and got reasonable performance. This is across a number of CPUs. There's no GPUs in this example. And you can see here that it's totally converged because I'm using a high-level abstraction of OpenMP SIMD essentially in order to get the performance. But not satisfied with that, I went back and did some manual vectorization using intrinsics, and that ended up with a code that performed much better, but it didn't perform. It didn't have. You can see I took a big hit in convergence, right? I had to do a lot of specialization to make that happen. Now after that, one of the things I was able to do was to introduce a new abstraction for those SIMD types, and then claw back a large amount of that convergence, right, while preserving performance. And again, this is a transformation these are realistic transformations I think that we can do in our codes, where you introduce a specialization at the cost of some divergence, and then you can refactor things in order to get back convergence without sacrificing performance or not sacrificing much performance. It's even possible, I think, in many cases to directly go to this blue point here, right, where you introduce the abstraction at the same time. BabelStream is a code from the University of Bristol. It's a collection of stream benchmarks, and this is a lot of it was written by Tom Deacon and Simon McIntosh Smith and others. There are a lot of implementations, and I want to say that there isn't a lot of effort to reduce divergence, right? This is really a way for them to test out different languages and different platforms, and there isn't any effort really to make this be a single code base. But it's still interesting to look at, and we can group things in different ways to have interesting results here. So we're looking at a set of CPU platforms and a set of GPU platforms all together. Again, there are many different codes here. What I'm looking at here is if you were to look at all the codes together and put them in a big duct tape code, right, you can see that you have nearly total divergence, right? The code convergence is very low, but the performance portability is at 1, right? If we look at just the OpenMP code, right, there's a target and a CPU type OpenMP code, and that introduces some divergence, but that gets a very high performance portability. Moving over to Cocos, Cocos once again is very nearly at code convergence of 1 and has a pretty high performance portability score as well, right? We see that same trade-off again, where there is a little more, a little less convergence for more performance portability that we see there. And then OpenACC and OpenCL have less performance portability than Cocos, but end up having a pretty similar convergence. They are essentially 1. In fact, those 2 points are basically on top of each other, which is why they appear as 1 dot here. Okay, so moving along from that, let's talk a little bit about how we can use these same plots to analyze large groups of codes. Because we're often faced with this where we have a number of platforms we want to support and a large body of code that we want to understand and characterize. We might want to know, for example, how this might reflect on tools that we're using or on hardware that we have. And also, perhaps as a cluster owner, you may want to say, how can we make it so that these codes run more efficiently on our cluster? This is totally synthetic data. It's just easier to present that way, and it's more flexible. So that's what we're talking about. We are using this inside Intel to measure the success of some of our software tools and our hardware. So we're using a methodology similar to what I'm going to talk about here. Okay, so we know vaguely that we want our codes to be in the top right of this type of diagram. How do we talk about this in a more quantitative way so that we can really compare 2 different results instead of just having point clouds? One such way to do that is to look at the minimum of performance portability and code convergence, and then bin those. So that's what we've done here. We've introduced 10 bins by tenths, or sorry, yeah, by tenths of 1 from 0 to 1. And we've binned every point by the minimum of its performance portability and code convergence. And you can actually plot that now as a 1D histogram. And you can extract some statistics, right? There are many different ways to compare these sort of things. But some of these things are very useful here. We can see that the median is 0.6, the minimum is 0.21, and the maximum is 0.91. So we have some idea of how our codes behave. Let's say we want to set a goal. Let's say, and this is similar to the sorts of goal that we've been setting inside Intel to track these things. Let's set a goal that 50% of our codes have to have a score of 0.8 or higher in this minimum metric. And then let's say that, for example, we've done some work on the tools, we've done some work on the codes, and we've improved things quite a bit. So this is the same code. These are the same codes that have been improved, either through tool improvements or through code improvements. So here you can see I've zoomed in here just to give you a better view of this area where all the data points are. And you can see here that the histogram, of course, looks much better, right? We have a median of 0.86, which means that certainly 50% of our codes are scoring 0.8 or higher, and our minimum is much higher, as is our maximum. So this is a sort of example of what we have looked at in a way that we can talk about these things and compare them with previous results. So to summarize, performance portability and code divergence are complementary, and we can combine them in a 2D plot, being careful about platforms and flipping divergence around to convergence to reveal interesting trends and patterns. And you can do this with single codes or aggregates of codes. This allows us to see where we are now, and we can also set goals about where we want to be. And then by understanding what sort of changes are needed to move in different directions in the graph, we can have a better idea of how we should be optimizing our codes and improving our tools. And like I mentioned earlier, these methods are being used inside Intel to better understand how our codes are performing, how our tools are performing, and how we can get to a more performance portable, productive future. For future work, we need more people to chime in about what sort of things are satisfactory to them, what sorts of graphs and what sort of milestones that they want to reach are that satisfy the results, because all of this is very subjective. Another useful tool that we'd like to explore more is varying platforms. So as you drop platforms or add platforms and look at how the data changes, you can understand, for example, if a platform is a weak spot, if you have tools that need to be improved or codes that need to be improved because they don't support that platform well. You can also do interesting language shootouts, similar to what I did with Babelstream, where you can look at how several different applications implement the same problem with different tools, with different languages, and we can see how they support platforms, whether or not they support fine-grained specialization or not. And again, as a community, we need to collect and publish more data so that we can do more analysis of this, and I want to do a call to action that we do that. Here are some legal disclaimers, and thank you for listening to my talk.